Hey guys, welcome to Ask Becca About Space. In this video, I'm going to address part 2 of Ashton's questions because she has 2 more questions. And I guess we can just dive right in. Let's do it. Okay. So Ashton asks, the third question is, do things shrink in space? Not spontaneously. Okay, because similar to what we discussed in the previous video about pressure balances and why stars implode and why anything would implode in the first place, things don't just kind of spontaneously shrink or spontaneously grow just because. There has to be a reason for those things to happen. Okay, so if for something to shrink in space, well, the pressure balance outside of the object would have to be much larger than the pressure of the object itself. This is easier to imagine if we think about a balloon, right? So let's say that I'm just holding a balloon on the surface of the Earth, and the balloon doesn't change size, right? Because there's no reason for the balloon to change size. The air that I put into the balloon has a similar density to the air outside of the balloon, and so that means that the balloon can be stable in its own shape, okay? Especially if I fill the air with, or fill the balloon with air from the room, well, there's absolutely no difference in pressure between the air inside the balloon and the air outside the balloon. So the boundary of the balloon remains stable, okay? But let's say that I would take my balloon up a mountain, and I would just hike up a mountain, a really, really tall mountain with my balloon. And at the top of the mountain, I might notice that now there's something different about my balloon. My balloon has changed its shape, okay? Why would that be? Well, that's because at the top of mountains, if they're tall enough, if you've ever been to the top of the mountain, you might have realized that it's a little bit harder to breathe up there, right? The air seems like it's a little bit thinner, and it is, because we have a little bit less of Earth's atmosphere on top of us, and the pressure of the air up there is a little bit lower. Okay, so now if I have my balloon and the pressure of the air outside is less than the pressure of the air inside, then that means the air inside wants to expand into equilibrium to make things equal between the inside and the outside of the balloon, right? And so that means that my balloon grows a little bit at the top of the mountain. And if it doesn't grow too much, then the balloon can still remain a balloon and it won't pop. But if that expansion is too much for the boundary of the balloon, for the rubber that the balloon is made out of, then it will pop, okay? So let's say that I just kept going. Let's say that there was a ladder that would take me all the way to space, and I just hopped on that ladder and I took my balloon with me. As the pressure of the air decreases and decreases and decreases, the gas inside the balloon is going to want to expand again to be equal to the pressure on the outside of the balloon. And of course, eventually my balloon will pop if that pressure gets too high. But let's just say, for the sake of argument, that it doesn't. That means that once I get to space and I'm above Earth's atmosphere, where there's essentially no pressure on top of me, that balloon will try to expand as much as it can. Okay, so disregarding any implications due to temperature, and just thinking about kind of the air pressure and how space in between everything is a near vacuum. It's not completely empty, but it's a near vacuum, and we can assume that it is a vacuum because it makes the math a little bit easier. Then my balloon would actually expand rather than shrink, right? And so just remember, to sum up, I guess the point of this question is that for things to shrink, the pressure on the outside needs to be larger than the pressure on the inside. And for things to expand, the pressure on the inside needs to be larger than the pressure on the outside. Because most of the time, everything just wants to be in equilibrium. Forces need to be conserved and things need to be balanced, right? This is kind of the way that we see nature to behave, right? Nature really wants a natural balance, okay? And so whether you need to expand to meet that balance or shrink to meet that balance, that's generally the behavior that we see, okay? So, all right, last question. I love this question. It's actually really difficult, so bear with me. This question is, do black holes have any effect on light speed? Welcome to my TED Talk on graduate general relativity. So the short answer is yes, and the short answer is also no. And the medium answer is it depends. Okay, so let's go. Let's just do it. All right. Black holes are probably one of the most fascinating objects in the universe. They are essentially what we perceive to be an infinite well of gravity. Okay. So when we think about gravity, there are a lot of different ways to kind of picture it in our mind. It's tempting to think of gravity in the sense of, oh, this is the thing that sticks us to the center of the earth. Okay, sort of. And then in another way, we can think about it as, oh, this is the thing that moves space-time and the thing that makes it curved. Okay, yeah, that too. Or we can think of it as this thing that sends these big waves and ripples through the universe. Also accurate, we're finding, especially with observations from gravitational wave interferometers like LIGO. We have detected waves from gravitational collisions and collisions of black holes, collisions of neutron stars that send that ripple of gravity waves through the universe. And so we know that those exist. They're just really difficult to detect and difficult to understand comprehensively. So forgive me for whatever ramble is coming out of this video, because it's just going to be a free-for-all at this point. So black holes mess a lot of stuff up, just in general. If we think about space as not just kind of an empty void, and instead as some sort of surface that's curved, then we can make the mathematics surrounding gravity make a little bit more sense to ourselves. Okay. And I think, I guess, to illustrate this, think about space and time as something that are these two entities that are connected, and think of them almost like a trampoline surface. You know what I mean? Like, imagine that you're standing at the center of a trampoline, right? And because the trampoline mesh is very stretchy and bouncy, your feet create kind of a well in the center of the trampoline. And that's kind of how we think about the way that massive bodies affect space-time, okay? Now imagine that your foot went all the way down and all the way down and all the way down and never stopped. That's how we think about a black hole, okay? An infinite well of gravity, okay? That curves and bends the space-time around it, okay? And what we figured out, we being a general collective and not myself particularly, is that light actually has to compensate for that curvature of space-time. This is something that's called gravitational lensing. If I'm trying to look at a star that is far away from me, and let's say that there's a gigantic galaxy or a black hole or something in between me and this star that I'm trying to observe, okay? That means that the light from the star has to travel essentially around this big gravitational hole to get to my eyes. And that means that the light that I observe from this star is kind of in the wrong spot by the time it gets to my eyes, because I'm seeing something that is curved around another body, okay? And I observe that light to be coming from somewhere else than it actually is physically located in the universe, which is just a bonkers thing to think about, okay? So don't get too lost in that. But what does this do to the speed of light? In one sense, it doesn't do anything to the speed of light, okay? As long as I am measuring the speed of light locally, okay? So wherever I am, whether I am here on Earth or whether I am theoretically sitting next to a black hole or whether I am essentially falling into a black hole, if I measure what the speed of light is to me, then I will always get the same number, okay? And that is the speed of light in a vacuum, which is taken to be a constant, okay? It works if space-time is flat everywhere. It doesn't work if space-time is curved everywhere, but it always works for me locally, okay? This breaks if I try to measure the speed of light someplace else, okay? So let's say that I am sitting pretty outside of a black hole and you are falling into the black hole, and I'm measuring the speed of light where you are. As you get closer and closer and closer to the event horizon of the black hole, which is the threshold at which nothing can escape, because that's where the escape velocity of the black hole is at or greater than the speed of light, okay? And the escape velocity is basically the speed you need to be traveling to get out of a gravitational field. And black holes are black because the escape velocity is greater than the speed of light, which is essentially the speed limit of the universe to a zero order approximation, okay? So if I am watching you, and let's do this thought experiment that's relatively famous. So let's say that you have a flashlight and you turn the flashlight on and off at equal intervals. Let's say once per second, okay? And I'm watching you approach the black hole and I'm measuring the time between the light flashes to be once per second. But as you approach that event horizon, I start noticing that the time between your light flashes is dilated. That means it's stretching out. That means that I'm actually not measuring a light flash once per second. I'm measuring once per every 2 seconds, and then 4 seconds, and then maybe 8 seconds, and then maybe 100 seconds, and then maybe, oh my gosh, a year between. Because the closer you get to that gravitational field, the longer time is stretched and dilated relatively, okay? For you, you are still observing a light flash once per second because you are local to the gravitational field surrounding you. So everything local to you is business as usual. But to me, time is being stretched so far between the two of us that I'm no longer measuring the right rhythm of light that you're sending me. And in fact, the wavelengths of the light are getting a little bit weird. And at some point, I can't even see you go over the event horizon because time is dilated so much that I could never even see you cross because it would take too long, right? So the point is, black holes are extremely complicated and extremely relative. And this is something that Einstein was very obsessed with, luckily for us. He realized in both general and special relativity that time and length are relative to the observer, okay, and the frame of reference to which you are observing, okay? Black holes have been kind of the center of a lot of interesting discussion, both in science, but also in pop culture. I don't know if you've seen the movie Interstellar, but it plays a little bit with this time dilation concept, right? The physics in Interstellar is actually pretty solid. I mean, obviously there are some creative liberties taken with like flying into a black hole and then ending up in a bookshelf and all of these things that kind of make time loop back in on itself. But the scene where they go down to the planet where there's these gigantic waves, and when they come back to the spaceship and years and years and years have gone by, that's solid, right? Because to them, just a couple of hours had gone by. But to the observer on the spacecraft, away from that intense gravitational field, decades had gone by, right? And this is the fundamental basics of relativity, okay? So to sum up, first of all, I'm sorry, this is very complicated and it's an excellent question. Second of all, the answer to your question is yes and also no. The thing is, the deal is that it depends on the observer. If I'm away from a gravitational field, then I might measure a different speed of light in that gravitational field. But if I am inside that gravitational field, I will always measure the same value of the speed of light. Okay, so that is the very, very basic introduction to gravity-based general relativity. Okay, excellent, excellent question. So good. Did my best for that one, but hopefully you guys learned a little bit of something about really basic general relativity and the way that black holes work. It's an open question. I have a lot of colleagues that are working on black hole related things and dealing with black hole related universes. For me, I just deal with the sun because that's what I like. But black holes are very, very cool. And if you're interested in learning more, I would read Einstein and I would read some Stephen Hawking, because he's really good at making these kinds of things very accessible to folks within science, but also outside of science. Okay, so again, Ashton, thanks for these questions. And if you guys have any more questions, because I'm sure I left a lot of room for more questions than I did answers in this video. Great. Please let me know. I'd be happy to do my best with all of these questions, no matter how crazy. All right. Bye.